Thank you. Good morning. So what I want to tell you today is what we can do from sensors and sensor networks for the problem of transporting food without losing it. That's called the Intelligent Container Project in Bremen. By the way, there also is a large intelligent container project here at the University in Busan, because Busan, like Bremen, has a large harbor and a large university, so they also have a lot of research in this topic. The outline. First, I want to give you a motivation. Why do we need sensor networks for the supply chain of food? Then the question is, what can they really do? Where can we help? What type of sensors do we need? And how many sensors do we need? And one special topic for sensing food, ethylene. I will come back why ethylene is so important. And very shortly at the end, communication in sensor networks. So the why. This slide shows how much food is lost on the world every day, and it's immense. It's more than 200 kilograms per year and per capita worldwide. How is it lost? A lot of it is lost by us, by the consumers. We don't care for what we buy. But a larger part, the gray one, is lost during supply chain, during transport. And now when you see in rich countries where there's a lot of food available here, we lose a lot by problems of the supplier. In countries where food is more valuable, like Sub-Saharan Africa, people take more care. So the red part, what consumers lose, is drastically less. But the gray part, which is lost between production and retailing, is not reduced. So there are obviously some real problems happening on the supply chain. And the question is, what can we do to reduce this? My favorite example is the banana. The main reason is we cooperate with the company Dole, which does a lot of banana transport from Middle America, Costa Rica, Colombia to Bremen. And we do a lot of experiments with our sensor networks on the banana chips. So this is the supply chain of a banana. You have the plantation. In the plantation, you grow the fruit, you pick it, you clean it, you pack it. Then there is transport from the plantation to the harbor. This part is extremely dangerous when the fruit are transported on lorries from the plantation to the harbor, because there are a lot of things can happen with acceleration and with temperature. Then the green banana are transported for 3 weeks on a ship. You have to be careful that the temperature, this temperature must be flat. They are still green. They are ripened in a ripening, which happens in Bremen or in Hamburg, and then they are sold. Our project in Bremen, where we work on it, we call it the Intelligent Container Project. It has been going on for several years. It's paid by the German government. It's altogether 20 partners, 3 partners from academia, 17 industrial partners, and the main partner for the banana topic is the company Dole Fresh Fruit. So if we look at supply chain problems, what could wireless sensor networks do? First is we can concentrate data. Today, you have 2 thermometers in a container. One where the cold air comes from the cooling machine, the other one at the door. And they continuously broadcast to the harbor, which is a lot of data transfer, which is not very valuable. What you want is to have 1 signal per day saying this container is okay. And if the container is not okay, an instant warning. Or 2 a day. So you need a system in the container which supervises more than 2 points and which is able to decide things are going okay or things are going not okay. The next topic is estimating risk. Early warning if there are problems. A warning if there are hotspots. This means part of the banana start ripening, emit heat. And a warning if there is a fungus infection in the container. And the next point we can do is estimating what is the status of the fruit. And we have this estimation, we could redirect the supply chain. When we know this container has a problem, take it first when containers are transported on. So also in the next 10 minutes, I will go through those points. What does early warning mean? This is the situation today. Imagine you have a quality problem on a banana plantation in Costa Rica. The fruit go to the ship, 3 weeks. In Bremerhaven, you open the container and you find tons of rotten banana. This happens, okay? You phone to Costa Rica, you have a quality problem, do something. But this takes 3 weeks. So when I phone today, there are 2 ships on the Atlantic which have the same quality problem. This means not tons, but hundreds of tons of banana with a quality problem. Now imagine I have the intelligent container system. The first signs that something goes wrong, I get a week after ship has left the Puerto Limon in Costa Rica. So I can instantly warn and I win 2 weeks of time. And this means I win 2 full ships of fruit because of the early warning. So this is a strong argument to have a sensor network which can give you early information. Hotspot formation. Why are hotspots in fruit so dangerous? Everything you eat is still living. Green bananas, even if you cut them, they are still living. When they stay green, they live slowly. Once they start to ripen, their metabolism is working faster and this generates heat. So as soon as a banana or any other fruit are starting to ripen, a lot of heat is generated. More heat than a cooled reefer can take out. So once they start to ripen, you cannot withhold it anymore. The temperature goes up and up. The emitted energy is larger than the energy you can take out. You have a strong nonlinear effect, and then the whole container is rotten within some days. We made some experiments whether we are able to predict such a thing. First, you have to predict it when you want to avoid it. So here we artificially initiate a problem in a container. We initiate the problem by opening the door. The container should be at 13 degrees Celsius, but here in the beginning, for 2 days, we open the door and it goes up to 16. So 2 different cases. Here, temperature goes up, but when we close, it comes back. Here, temperature goes up a little bit more. Fruits start to ripen, and when you close, you cannot bring it back. It goes to higher and higher temperatures. And that's a hotspot. The interesting thing is, when you have this part of the curve, you can predict the rest. So when I know this part, and I use a model which has information about the thermodynamics of a container and about the biological behavior of banana, then I can predict the rest. And also, already after 2 days, I'm able to say this will be a problem or this can be cooled back and will not be a problem. What you need is strong knowledge about the behavior of the banana. So if you know the temperature history, what is going to happen? And one of our partners in University in the Netherlands is focusing on doing those behavior for banana. Another one is ATB, an institute in Potsdam near Berlin, who look for the biological models. What is the use of biological models? I can predict shelf life. Shelf life means I know this fruit has 3 weeks shelf life, so in 3 weeks I can sell it. After 3 weeks, stop, it's old. But of course, doing 1 point in time is very crude. Actually, it's something dynamic. So what I want to do is re-estimates the remaining shelf life dynamically based on the history of the fruit. That's a typical curve of those biological models. If you increase temperature, the period which you can keep the fruit green will decrease. There's also a branch on the other side. If you decrease temperatures too low, let's say 1 or 2 degrees Celsius, normally fruit will have a freezing problem. They will decay very soon also. And you must implement those nonlinear models in this shelf life estimator. Then you must give him the information about temperature, the information about humidity, and about gases. And one more information about the look of the banana. I'm coming back to this point. What do I do with the remaining shelf life estimation? Classically, logistic people have a paradigm which is called FIFO, first in, first out. What comes in first goes out first. We want to have a new paradigm. It's called FIFO, first expire, first out. Those fruit which have the least shelf lifetime go out first. And I go one step further. I call that dynamic FIFO. Dynamic FIFO means that the remaining shelf life is estimated dynamically based on temperature, on the development of the banana, and based on the information I can get from them. What does it help? Here I've been displaying 4 model calculations made from different groups. Those are not experiments, logistic experiments, but those are model calculations based on supply chain modeling. The blue bars are classic supply chain. This means no quality information, just FIFO, FIFO, first in, first out. And you see that you have a strong loss on the supply chain. So 2 of them are for meat, 1 of them is for fish, and 1 of them is for berries. Berries are the most dangerous thing for logistics because they easily suffer from mold. Your problem is if there is not enough humidity, they dry. If there is a little bit too much, there will be mold. So berries are very dangerous. And next, I tell the model, readjust the supply chain with some knowledge how the fruit are doing, and model again the new supply chain. And you see that you can save roughly 50% of the loss in the model calculation. There are not enough real logistic experiments nowadays to tell how much I can realize in reality, but it looks quite good. I think we really will be able to reduce losses. So, what sensors do I need to do this? What do I have to sense? The most important thing still today is temperature. Normally, logistic people do not know enough about the temperature of their transported goods. Why not? They have 2 temperature sensors in a container. But imagine a container being the top container on the North Atlantic and cold wind is coming. You have 2 temperature sensors which say 13 degrees. But on top, on the ceiling of the container where the cold wind is coming, it may be 5 degrees only. What happens then? You measure 13 degrees. The iron ceiling has 5 degrees. So there will be humidity and it will drop down. So you may have a microclimate in the container, which is like rain, water dropping down from the ceiling, and you do not see it by temperature sensors. What we do at the moment, we supply many temperature sensors. For research, that's okay. We have 50 in a container. But then, to apply the systems, we have to reduce again. At the moment, our aim is on the long run to have 5 temperature sensors in the container and to be able to supervise the whole thing. What else can you get from the transport? Humidity, of course, O2 and CO2, that's to know what the atmosphere is doing. CO2 tells you something, whether the fruit are breathing, whether they have metabolic action. There may be accidents, so you also need an accelerometer. Why is that? It very often happens that a container is just dropped. It's taken off from a ship by a crane on the harbor, and then 20 centimeters above the concrete floor, they drop it. And this is disastrous for the fruit. So you need acceleration measurement. You need to know something about the biological variability. Mainly this means color. Today, in the port of Puerto Limon, they have a poster on the wall. Yellow banana and green banana. And there's a very famous about 10 pictures, and one is more green than yellow. And when you stick more green than yellow, this starts to become dangerous. But this is by eye. So what we did, one of our partners, is to make a small color sensor. It's a handheld. You go to one of the bananas or to several, put it there, and then you get a quantitative information about the color. Then you know what you loaded, biological variability by loading. And the last thing is, can we ask the fruit how they are doing? Does a fruit tell me what's happening? And it does. And the clue to this information is ethylene. Ethylene is a gas which is emitted when fruit ripens and which makes fruits ripening. So most fruits emit ethylene when they start to ripen, but when they feel ethylene, the ripening is initiated. You know the effect. Put a ripe fruit between unripe apples or tomato. Next day, all of them are ripe. So they communicate. They want to ripe simultaneously. And this is done by ethylene. So, ethylene is a gaseous hormone of fruits. It's a very simple molecule, 2 carbon, 4 hydrogen. And this is a typical behavior. When fruits are pre-ripening, we call it preclimacteric. There are 2 types of fruits, non-climacteric fruit and climacteric fruit. Climacteric fruit means they can stay unripened very long, but once they start ripening, it's irreversible. They go through until decay. It's not a continuous process. It has an onset, and once the climacterium is there, you cannot stop it anymore. Many fruits, like apples and banana, behave climacteric. So you have preclimacteric fruit, and here you have a slow rise of ethylene, and you have to measure in the part per billion range. Once you have the climacterium, it rises drastically, and here you can measure in the part per million range. There are sensors for this. There are no sensors in the part per billion range. You need sensors which are very sensitive, part per billion, and very selective. Because in a container with apples there's everything, esters and alcohols, so a lot of organic chemistry in the ppb region. So it must be also selective. The method to do it, to measure this, essentially there are 2 methods. You could use infrared, non-dispersive infrared sensors, or you could use gas chromatography. We did both. Infrared works quite fine to around 10 ppm. So infrared is good here. But it was not possible to come here with infrared. So you use a gas chromatograph. Gas chromatograph are standard equipment. You can buy it. It's this size. It costs $40,000. And it needs a technician to use it. So you need a gas chromatograph, which is small, is autonomous. You need no technician to use it. And it should be cheap. We aim at $900 per item. You can do this with micro-machined systems. You know that a lot of people have made miniaturized gas chromatographs, mostly using micro-machining for the chromatographic column. So the essential thing of a gas chromatograph is this separation column, where a long tube where the gas is adsorbed and desorbed again. And you check the adsorption and desorption time to separate gases in time. What you need here is not only the column. Of course, you need a gas sensor in the end, like every gas chromatograph. You also need a pre-concentrator. Otherwise, you cannot go to the ppb range. A pre-concentrator is also in silicon etched a small reactor. What it does is it collects the ethylene. So you pump the container air through for 20 minutes. It collects all the ethylene it can get. And then it sets the ethylene free fastly to boost a short but very high pulse. How do you set it free? By heating. So at room temperature, the system is collecting. When you heat it, it sets free. This is a typical system, so it's about this size, and it's a complete gas chromatic system. This is the column. Can we really go down to the part per billion range? Yes, we tried it. We can do that. What you see here is a test measurement with a 400 ppb mixture from a gas bottle. Ethylene in air. And the blue curve is the measurement. This is the ethylene peak. There's a much larger peak, which is water. The big problem for the specialized microgas chromatograph for ethylene was to separate the ethylene peak from the water peak. So we had to do a lot of experiments with different stationary phases, so with different adsorption materials to get this separate. Now it worked. So with 400 ppb, you have a very well visible peak. Our conclusion is that we can go down to 10 ppb using that. Interestingly enough, the age of silicon etched gas chromatic columns may be over before it even began, because today there's a new solution. So we don't etch silicon wafers anymore for the columns, but we just print them. So we have a 3D printed version, which is also able to print this very, very long tube. And if you collect the right polymer to do it, you really can have the same gas separation. So this is also 400 down to 400 ppb ethylene is the blue curve, and you can see some 10 ppb ethylene could be very well separated. So we know what the fruit wants to tell us, and this is essential for the whole thing. That's the best information that something is going wrong, that ripening is going on, and then you can act or warn. Very shortly about communications, this would be a topic on its own. Only one message. Everybody goes to high frequencies, we go to low frequencies. Why? When you have fruit in a container, you have water. Water means damping of electromagnetic waves, and the higher the frequency, the worse it is. So you must go below 1 gigahertz to come through. Everybody else moves to several gigahertz. This will not work in food logistics. And I conclude, what can wireless sensor networks do? We can assess a risk, say, this container will have a problem in 2 weeks, or it already has a problem. We can make a continuous re-estimation of the remaining shelf life, and this may be the beginning of a paradigm change in logistics from FIFO, first in, first out, to FIFO, first expire, first out. What sensors do we need? We measure temperature, humidity, also acceleration. And the clue to know what the fruits do tell us is gas sensors, micro gas chromatography for ethylene. What remains to be done? There are transfer projects of our industrial partners about sensor nets, sensor nodes being sold soon. Some logistic companies start implementing dynamic FIFO. And what do researchers do? There's still a lot of logistic impact really to understand the impact of the intelligent container on logistic processes. Next point, a big open question. There are two big open questions. First big open question is how to power sensor nodes. We use batteries, there's nothing else. So might it be possible to use energy harvesting for sensor nodes? At the moment, it's not possible. And from sensors, fungus infection is the next big topic. We are developing systems which can tell us there is fungus growing or there's a danger of fungus. I'm not going into this, but Roland Blank from our institute today in the afternoon will have a talk on the problem of fungus infection of containers. Yeah, thank you. Questions?